Now, there's a number of properties of conjugates with complex numbers that make life a lot easier to deal with as you go through, and it's helpful to know these results as well. So the idea that if you've got the conjugate of the sum of two numbers, conjugate of sum of two numbers, is the same as the sum of their conjugates separately. And again, if you got the subtraction of two complex numbers and you take their conjugate, it's the same as taking the conjugate of them separately. Multiplication of two numbers and then take their conjugate is the same as multiplying and having the separate conjugates. And then the same with division. Divide two complex numbers and take their conjugate. It's the same as the division of the first conjugate by the second. So what we want to look, and we'll prove one of these. You can see all these proofs. A couple of the textbooks will go through these proofs. So you can, again, if you know the proofs, it's handy to know. But really what we wanted you to do is use these properties as we go through and do problems later on. So a proof of one of the properties. So let's pick three to start, for example. So if you've got Z1 and Z2 of these two complex numbers, x plus iy, a plus ib. So again, multiply them out because we want to prove that the conjugate of the multiplication of both is the same as the multiplication of the conjugate of each. So we multiply it out, x plus iy, a plus ib, expand it out, and we get this situation. Because we get iy times ib is minus by, we collect our real parts and collect our imaginary parts. So if we look at that situation, and we just get our brackets around that one as well. So and we look at that, that's a real part, that's our imaginary part. So if we take the conjugate of it, all we're doing is changing that positive to a negative. What effect does that have on it? So let's have a look. We get ax plus by minus iay minus ibx. So when we multiply both of them by I. So again, we split them up. We get the x's together. So what I'm really doing is just factorizing in the pairs here. So get our x's together, ax plus minus ibx and minus iay minus by, and factorize the x out, gives us a minus ib. Factorize the minus iy out, gives us a minus ib. And because we've got a common common factor of a minus ib, we can factorize out. Remember that minus by, when we factorize minus iy out of it, the iay goes, so it's just a, but I minus ib times minus iy gives us minus by from up here. So remember that. That's how we can be able to get back to that factorization, which sees that that's the conjugate of z1 and that's the conjugate of z2. So there's our proof. Again, not really needing the proofs a lot of times. Should be able to try and prove it, but what we really want you to know is that you can use those results as you go through. So go back and be careful. If you want to look at more proofs of all these, go back and have a look at the text. A lot of the text or on the net will give you the proofs. So, but again, it's more about the results we've got here rather than the actual proofs of what of the properties.